Welcome everyone to our next Master Lecture in the GoFly Master Lecture Series. As everyone knows, Boeing is grand sponsor of the GoFly Prize, and of course we are so pleased to be joined by Pratt Whitney as our corporate sponsor, as well as over 20 aerospace and STEM organizations around the world. It is my pleasure to introduce Geoff Hunt, who is our Master Lecturer today. Geoff is Senior Vice President of Engineering at Pratt Whitney. He leads Pratt Whitney's global engineering team with a focus on delivering customer requirements, developing technical leadership, and advancing technology development programs that will support the next generation of commercial and military engines. Hunt's 34-year career in the aerospace industry has included leading roles in the development of landmark products, primarily in the area of large commercial aircraft. He was most recently Vice President, Engineering and Technology for UTC Aerospace Systems. In this position, Hunt led product development programs to ensure UTC Aerospace Systems continue to offer differentiating technologies to meet customer needs, as well as ensuring flawless engineering program execution by leading the implementation of best practice processes, tools, and resources across the enterprise. Geoff began his career as the engineer at Rolls-Royce, where he spent 13 years working on large commercial engine development programs before joining United Technologies. His past 20 years of experience include roles of increasing responsibility in engineering and program management at both Pratt & Whitney and at UTC Aerospace Systems, where he provided leadership across a large range of products and platforms, including product development, system integration, and program execution for the 787 Dreamliner. Geoff holds a bachelor's degree in mechanical engineering from Sheffield University in England and an MBA from Boston University. He is also a fellow of the Royal Aeronautical Society. It's my pleasure to introduce Geoff Hunt.
Thank you, Needy. Well, good morning, everybody. Put some slides up here. Well, at Pratt & Whitney, we're delighted to be a corporate sponsor of GoFly, as well as the sponsor of the Disruptor Award, recognizing originality, innovation, and groundbreaking ideas in the competition. I've been tremendously impressed with the progress made so far by the GoFly teams and the diversity of ideas and approaches to the problem. In my talk today, which I entitled More Power to You, I thought that I would look at how disruption has influenced the aero propulsion space over the past century, how it continues to shape the propulsion landscape, and hope it gives you some things to think about as you develop your aircraft. Pratt & Whitney and the newly formed Collins Aerospace are the aerospace divisions of United Technologies. While Collins is a leader in the supply of airplane systems, Pratt & Whitney has been in the business of aerospace propulsion for the past 93 years. Within our military engine business, we design and manufacture high thruster weight engines for aircraft such as the F-15, F-16, F-22, and of course the F-135 engine for the Joint Strike Fighter. In our commercial engine business, we power many of the large commercial aircraft that you might fly on today. And in the past decade, we revolutionized commercial flight with our geared turbofan series of engines, which I'll touch on more later. Finally, our Pratt & Whitney Canada business powers many of the general aviation and business aircraft in service today, with engines such as the PT6, the gold standard for turboprop engines under 2,000 horsepower. Before I get into my talk, I'd like to show you a short video by way of introduction to Pratt & Whitney.
For human progress. An instrument to rise above boundaries, connect people, grow economies, and protect the world. Together with our partners, we work with an explorer's heart and a perfectionist's grit to advance it. The magnitude of flight both humbles and motivates us. It demands vision and relentless attention to detail. Requires dependable teams that deliver the highest quality products and services, and empowered people willing to do the right thing in the best interest of our customers. Every day, we rise to that challenge with state-of-the-art engines that carry people reliably to their destinations. Service experts who provide the care and intelligence to keep planes flying, and generations of innovators working together to transform aviation. We love what we do because we believe flight unleashes the world to go beyond.
So before I get into the details of propulsion development, let's look at it in the context of technology as a whole. First, let's look at some technology curves. What you have here is a log normal plot with a logarithmic y-axis on the left and a linear time axis. So these curves are going to look linear, but are actually exponential technology curves. Let's look at jet engines first. On the time scale that we have here, it's basically flat. One way to describe the slope of these curves is through doubling times. That is the time to double the cost performance of a technology. And so for jet engines, the historical doubling time going back to the beginning of the jet age is about 60 to 70 years. Said another way, it takes half a century to halve the specific fuel consumption of jet engines. Now let's look at some other mechanical type products. Rooftop HVAC units, a little steeper, but also pretty flat. Here, the cost performance doubling time is around 25 to 30 years. Shifting products again, for elevator coated steel belts, we're looking at 15 to 20 years doubling time for the tech curve. So the bottom line is that these mechanically based technologies are relatively slow moving, driven mainly by improvements in materials. Increasingly, however, we see the intersection of these mechanical technologies with a landscape that is much, much faster moving. Digital technologies, and these are all hardware, not software, all evolve at approximately the pace set out by the famous Moore's law, a doubling time of every 18 to 24 months. Electrical technologies are also interesting. I think these are also fairly slow in their pace of evolution. Recently, however, there's been a huge influx of investment from consumer devices and automotive into electrical technologies. And so the doubling time for battery technology is around 5 years. And lastly, if you look at some of the advanced manufacturing technologies like additive and synthetic biology, while slower than their digital counterparts, they're still faster than what we are used to in the propulsion space. I'll come back to talk about how some of these intersections are disrupting our industry, but first let's go back in time and look at some of the key disruptors over the past century. Disruption is not new to our industry. The propulsion business 100 years ago was largely based on water-cooled radial engines at about 300 shaft horsepower. As we moved into the 20s, we saw engines such as the Pratt Whitney Wasp, pictured here, introduce air cooling to the radial piston engine, enabling a step change in thrust-to-weight ratio. The variable pitch propeller was a concept that many had studied since the first airships, but it was developments in hydraulic actuation that made it practical in the 1930s, dramatically changing the takeoff and climb characteristics of engines. The jet engine, in development in the 1930s, was first introduced in the 40s in aircraft such as the Messerschmitt 262 and the Gloucester Meteor, and again enabled a whole new approach to aircraft design in terms of speed and range. So picking up from the evolution or the introduction of the jet engine, this chart shows how technology subsequently progressed within the large commercial engine market. Picking up from that pre-war single shaft jet engine, you see we have the ability to step up gas turbine efficiency by about 10% every decade or two, with step changes in engine architecture, and then periods of incremental improvement in between. In the 1960s, we saw the wide application of dual spool jet engines like the J88, allowing a more efficient way to achieve higher operating pressure ratios. Then in the 1970s, structural, aerodynamic, and materials breakthroughs led to the high bypass ratio engines that powered wide-body aircraft such as the 747 and Lockheed TriStar. And more recently still, we've seen bypass ratio double from 6-to-1 to 12-to-1, bypass ratio being the ratio of the core to the fan of an engine, again, driving tremendous efficiency improvements. It all amounts to that doubling in technology in half a century. So how do we use this technology today? What I talked to is the large commercial story, but there are many different markets under the broad heading of aero propulsion, as illustrated in this graphic. We define the aero propulsion market to include commercial and military aircraft, helicopters, business and regional aviation, agriculture and general aviation, UAVs, auxiliary power units, and a range of turboprop applications. And of course, today we look increasingly at the personal taxi space. The design drivers associated with these applications vary considerably. I make this point to emphasize the importance of really understanding the mission and market demands that must guide your thinking in the selection and development of propulsion architectures and the wide range of areas where disruption can play out. For example, looking at a sample list of design drivers, a military jet will demand high thruster weight, high operating pressure ratio, and low observability. Whereas a large commercial engine might put priority on fuel burn, noise, and emissions. And a short-haul commercial aircraft will live or die based on the reliability with which it can hit its turnaround windows. Of course, in all cases, safety and cost are critical, but how that is achieved for a given duty cycle may vary. So let's dig in a little bit to how we go after some of these design drivers with our technology planning, starting with efficiency. When it comes to engines, there are two areas in which we focus: thermal efficiency, the efficiency with which we convert the energy and fuel into useful work, and propulsive efficiency, the efficiency with which we use that work to produce thrust. Over recent decades, much of the focus in the area of propulsive efficiency has been around fan aerodynamics and increasing bypass ratio. But the most recent commercial engines from Pratt Whitney have seen a significant improvement in this area through the introduction of a gear between the fan and the turbine, the so-called geared turbofan. Pratt Whitney invested billions of dollars in the development of this technology, which changes the architecture of a conventional turbofan engine by introducing this gear between the low-pressure turbine and the fan. In a conventional engine, the turbine drives the fan on a common shaft, and so they, by definition, rotate at the same speed. However, for optimum efficiency, the fan will typically want to run slower than the turbine, and so by introducing a gear, you can rebalance the core and achieve much higher efficiency levels. This is easier said than done, hence the investment levels, but the prize is huge. As you can see from the chart, over the past decade, we've seen improvements of 16% of fuel burn, and I can tell you from experience, if you go back over my experience in this industry, in 30 years, we would eke out for 2%, 3%, 4% would be a tremendous achievement. 16% is truly revolutionary here. Dramatic reductions in carbon dioxide and NOx, footprint for noise reduced by over 70%, and as you'll see, 1.5 million annual cost savings per aircraft, and that's a combination of lower maintenance costs and the fuel burn that's involved. So as I said, the other part of the equation is thermal efficiency, which largely comes down to how high a pressure ratio you can drive through the core. Driving pressure ratios in the core of the order of 30:1 within an acceptable core package is a challenge aerodynamically, structurally, and thermally. But it's in the development of materials, design, and cooling system to handle this challenge that demands real technology development. As illustrated here, we're talking about temperatures sufficient to melt rock or steel and loads equivalent to hanging an airplane off a single blade. And as we drive for ever improved thermal efficiency, these challenges go up. You could look at the challenge as the application of three levers: development of ever more capable materials, the process through which those materials are produced, and the design of the cooling systems and coatings to provide additional capability. This chart gives some insight into how we think about materials. The first jet engines ran at a peak temperature of around 1200 degrees Fahrenheit. They had aluminum alloy compressors and stainless steel turbines. The development of nickel alloys allowed temperatures to increase, and a series of important breakthroughs have pushed today's engines up into the 1800-2000 Fahrenheit range. You'll see in the center of this graphic how the nickel alloy section moves from forgings to castings and starts to neck down towards the higher temperature ranges. And this has been achieved by these progressive improvements, things like managing the grain characteristics of the alloys through directional solidification, and then single crystal materials to ensure capability. Cooling schemes, including ever more sophisticated film cooling, increase capability further. And then the application of thermal barrier coatings gets you to the very highest temperature capabilities with that type of material. The latest developments, which are moving the state of the art into a whole new arena, is the application of ceramic matrix composites for the highest temperature areas, the engines. You can see from the curve that this is really getting you into this whole new space. So that's efficiency, propulsive efficiency, thermodynamic efficiency, and we're seeing progressive evolution followed by steps of disruption as we introduce new mechanical and thermodynamic concepts. Shifting now a little bit about cost and speed. It almost goes without saying that cost and development speed are key drivers in our industry. And while there are many levers that one can look to, the rapidly evolving field of additive manufacturing presents some of the more interesting opportunities. One thinks about this in a number of different ways. Early applications have used the ability to iterate quickly to greatly accelerate development cycles. But the opportunity to minimize buy-to-fly ratios, the ratio of raw material to the actual material in the finished product, and the ability to combine functionality or simplify manufacturing processes in areas like complex brazing all mean that this will continue to challenge the norms of manufacturing in the industry. Early wins include things like fuel nozzles. These traditionally have been constructed through a complex brazing process that involves multiple cooling and heating cycles to put together a Russian doll-like assembly to create complex flow passages. An additive approach can greatly reduce the time to construct such a structure while assuring tighter process control and quality signature. In fact, it's amazing how much of our current design thinking is constrained by the capability of traditional manufacturing methods. For example, in the last few years, I had cause to review some interesting challenges related to cavitation in gear pumps. As we dug into the subject, it became evident that much of our design systems and tools were based on the capabilities of gear cutting machines at the time. But as we challenged the art of the possible with the latest additive techniques, we opened up a whole new realm of possibilities for improved gear efficiency. The importance of designing for the latest technology, or even challenging the manufacturing space to innovate to match the needs of your design, is clearly paramount. Finally, I wanted to touch on reliability and safety, a non-negotiable in the development of a propulsion system. There have been several discussions on this topic over the course of the GoFly lectures, and while I don't propose to go deeply into the topic here, a talk on propulsion would not be complete without some reference to the particular challenges that an engine faces in this space. Clearly, the loss of thrust due to an engine failure has to be considered within the course of the design process. Redundancy in the airframe and engine architecture is a key mitigation, either through the sharing of work across multiple engines or through redundancy of systems and monitoring of health at the engine level. Detailed analysis of the system's safety and failure modes and effects is critical, which will drive the measures required, including not just design, but the level of manufacturing and quality control of critical parts. You can see from the chart on the left how the reliability of engines has improved over time. If you go back as recently as 1980, all transatlantic flights were made by 3- and 4-engine aircraft. And as the joke went at the time, the reason I fly 4-engine aircraft is because they don't make 5-engine aircraft. ETOPS ratings, the ability to fly a twin-engine airplane a certain distance from a diversionary airport, has developed from a baseline of 60 minutes in the early 1980s to as much as 370 minutes today. This is enabled by a tremendous improvement in engine reliability. An important measure of reliability is the in-flight shutdown rate, which is exactly as it sounds, the average rate of engine shutdowns in flight for a given type. This has improved by 2 orders of magnitude since the mid-60s, driven by a relentless focus on margins, reliability, and learning. The testing a modern engine has to go through continually evolves and builds on the lessons of the past. By way of example, I included here a video of a bird strike test that we recently provided to the Smithsonian as part of a display that they put on recognizing the 10th anniversary of the Miracle on the Hudson. The bird strike test, where we have to demonstrate continued operation in the event of multiple bird strike, is just one of a range of arduous certification tests that must be completed before an engine can be certified for carrying passengers. Endurance testing at redline conditions, in-flight starting, cold weather and operation in icing conditions, and containment of a released fan blade are just some of the cases that must be demonstrated before an engine is deemed airworthy. Those of a sensitive nature may want to get a coffee while the video runs. So, whatever the mission for an aircraft, the levels of safety and reliability within the propulsion system must be at least as good as what has come before. And these are extraordinarily high levels in the industry today. So, I've looked at some of the drivers of propulsion system design to date, and certainly these will continue to be critical as we move forward. But there are plenty of other factors. And given time constraints, I haven't, for example, touched on how the latest developments in data, connectivity, and model-based systems engineering, for example, continue to instruct our thinking. But for now, I'd like to turn to a more disruptive opportunity that presents itself today, namely electric propulsion. Much has been published in this area of late, and there is not time in this lecture to dig deeply into the topic, but a few thoughts. Firstly, some basic economics. The chart on the left looks at a variety of substances in terms of their energy density on either a mass or volumetric basis. You'll see that Jet A, normal aviation fuel, and goose fat are broadly equivalent in volumetric terms. Natural gas and honey sit at about half that level, and way down there in the corner sit today's batteries, and indeed tomorrow's batteries don't get much out of that corner. So what's important to note here is that only goose fat and Jet A are in wide use today as fuel to power flight. So, how does electric buy its way in? You have to look at how system efficiencies contribute to the cost of converting that stored energy into useful work. You can see on the right of this graphic, the modern gas turbines at 55% efficiency or thereabout are phenomenal machines, nearly twice as efficient as a turboprop. So in financial terms, if fuel was, say, $2.10 a gallon, which equates to about 5 cents a kilowatt hour, an Aero engine will do work for about 10 cents a kilowatt hour at that efficiency level. The turboprop is going to cost nearly double that, up to about 19 cents a kilowatt hour. Now, if you switch to electric, the raw cost of electricity may be higher. I live in Connecticut, where we pay around 20 cents a kilowatt hour today. But if you go to the bottom of the range around the country, let's assume you can get electricity at 10 cents a kilowatt hour. With a 75% efficient electric powertrain, your cost per unit work is going to be about 13 cents a kilowatt hour. So better than a turboprop, not quite as good as an Aero engine. Finally, we might look at a series hybrid where you try to overcome the challenge of that battery storage by burning fuel in a thermal engine to make electricity to drive an electric motor. In some regards, we see this as the worst of both worlds, as you carry the lower efficiency and weight of the thermal engine in addition to the electric system. On just an efficiency basis, it trades poorly in our view. Of course, as commodity prices vary, this overall calculus moves around. Today, Jet A is actually closer to $5 a gallon, which will clearly make the electric option more attractive, assuming you can overcome that troublesome energy density issue. So how does this look when you lay it on top of a number of aerospace segments? On the smaller end of the market, particularly in the regime of the go-fly competition, the economic benefit of electric power at about the 0.5 megawatt level perhaps, and below, may trade favorably in a package that's practical, even rising to a larger 4 to 6 passenger craft, which may be closer to the megawatts sort of level of demand, could be interesting. However, above that, foreseeable battery technology starts to become problematic, which is why you start to see the series turbo electric systems enter the discussion, in a range of maybe up to 4 megawatts or so at the maximum end. For us as a large engine manufacturer, of more interest here is the opportunities that might be afforded by a parallel hybrid architecture. In this case, an electric motor provides supplemental power to a gas turbine as the prime mover. The level of power required in such a case could vary widely depending on the duty cycle, but this is an area where a sibling company, Collins Aerospace, has a strong capability, so we're studying a range of potential architectures with them. To give you a flavor for that, in its simplest form, one might consider the case of just adding an electric motor to the high-pressure spool of a traditional gas turbine. In such a case, you could use the motor to supplement power at the top end, allowing the engine to run cooler and extend life. Or perhaps you could size the engine to deliver power at a design point and use the motor to supplement for takeoff and climb, thus delivering a cost and weight benefit. A step beyond this would be to put motors onto both the high pressure and low pressure spools. It's a very interesting concept that would allow one to use the motors to not only supplement power, but also to manage the operability of the engine. Today's gas turbines have shafts that are thermodynamically coupled, meaning that they follow each other by virtue of the pressures and temperatures in the system. This typically requires bleed valves and variable geometry to run the compressors at an acceptable operating condition. If one can use the motors to manage the shafts to a particular speed, you may be able to dispense with the cost and weight and complexity of these ancillary systems and have a much more responsive motor. Finally, as you continue to extend this line of thinking, you start to look across the overall airplane system and ask questions about the full system architecture. Which of today's backup systems may become obsolete in such an architecture? How would power sharing work at the aircraft level? We're in the early days of these studies, but surely there's more to come in this space. So I hope this brief tour of the evolution of propulsion has been of interest. Clearly, there are many critical technologies that I haven't touched in this talk, and I apologize to the innovators and engineers in those fields. I started by highlighting the traditionally slow pace of technology development in the jet engine world, paced largely by thermodynamics and materials. But while this is true in aggregate, in detail it's made up of a series of radical ideas interspersed by years of incremental evolution. It's a highly technical field that requires a robust constitution in order to place those bets that enable step changes in performance, like the geared turbofan. But these changes are critical to achieving the ever higher standards of efficiency, emissions, noise, cost, and time to market that our customers demand. So as we look to the future, Pratt Whitney is proud to be the sponsor of the Disruptor Award for the Go Fly competition. We're looking for that idea that's truly original, innovative, and groundbreaking that might be the next rung on the ladder. I look forward to seeing how this develops, and more power to you. Thank you for your attention.
Thank you so much, Geoff, for such an incredibly informative presentation. We have a couple of questions coming your way. The first is, what are the fundamental physical phenomenon that make really small turbines so inefficient?
Oof, that's an excellent question. Small turbines. I think it's more what makes props so efficient in that space. I think I'd have to think through. You got me cold there, but I would think it's how you scale down in Reynolds number going down and how that's going to scale down in the efficiency levels in the compressors. That would be my starting point on that. I could think through it in more detail, but
okay. We'll move on to the next question in the meantime. So you mentioned that turbine technology has doubled in pace in the last 50 years. How would you compare the pace of tech development between internal combustion and turbine technology? Does internal combustion have a future in aviation?
I think it's probably less likely to have a future. I think the efficiency levels that you can get from an internal combustion engine, and in particular the way it's going to lapse as you go to altitude. The effects of altitude on an internal combustion engine really make it less and less practical in most spaces. There may be some spaces where it applies, but when you're talking about the full altitude range on that Aero Propulsion is going to require, the internal combustion engine starts to run into some real limitations.
And do you see open rotors or unducted fans taking over in efficiency-driven applications? What redundancy options are possible besides multiple engines within a turbine, for example?
I think that sounds like a couple of questions.
Yeah.
I would say, open rotor designs, we've been looking at open rotor design for a long time. Again, in this space, it's possible. We've spent some time looking at that development, but there are challenges that come with an open rotor that have kept it out of the market. So I think the industry is going to continue to look at it. I don't see an open rotor in the near future coming our way. The question about redundancy was a good one. A conventional, I talked a little bit about large commercial and the conventional architectures. As we look in the space that we're talking about here with smaller taxis, particularly electric propulsion, that tends to lend itself to multiple rotors, and in particular, how you can distribute propulsion for efficiency. So you get a sort of a double benefit as you can get to an electric driven system by putting more rotors on the system. You can spread out the efficiency of the propulsors overall, but you inevitably pick up the redundancy benefits that go with that. If you do that, you can do it mechanically as well, but it becomes a heavier, more expensive, and potentially tougher putt on the reliability front because you've just got so many mechanical connections running in that space. So I'd attach that sort of proliferation of rotors towards the electric propulsion space.
You mentioned costs of electric power. How does that change, or did it include overhaul or cell replacement costs on a per kilowatt hour basis?
So the numbers I was talking about are purely operating costs. As you get into life cycle costs, there are clearly many different ways to attack that problem. Whether you're getting into, let's say, cell replacement, recharging capabilities. To be honest, I'm not expert in the relative costs in the industry of those pieces of the life cycle. So I'm probably not qualified to really pass judgment on it. But I will tell you that in the studies that I've looked at, this business of what it's going to take to recharge batteries within a sort of an ecosystem of electric propulsion becomes a really interesting topic of discussion. You start getting into the sort of turnaround times that you need to make electric powered taxis viable. You're moving an awful lot of energy into a battery in a very short period of time. So you start getting into cooling connections. The connectors that go with these charging systems become very large. I've seen, examples where you actually have to use actuation to help engage the connectors because they just become so big that you can't humanly plug in. So a whole interesting space, not one that I'm particularly expert in though.
Okay. The next question is, you had mentioned integrating motors into turbine spools. How close is that to happening? What is the TRL?
Well, I'll say it's a you can do this in a couple of ways, whether you integrate it into a spool or you drive it through a gearbox. It's pretty close. You know, we can do this sort of thing, you know, in development test beds. It's still relatively early TRL, but there are demonstrations going on around the world of this type of technology. I mean, in its simplest form, you look at a 787 today. You've got a motor generator there that's used for starting the engine. That's putting driving the generator drives as a motor. It drives the HP shaft through the starting regime. So in that sense, it happens today. Expanding that to the case where you actually build a motor into the spool of an engine is something that I think is still a little ways off. I mean, there are considerations for maintaining, you know, for cooling a generator like that. There are reliability considerations. You start burying electrical motors deep in the core of an engine, they better be as reliable as the core of the engine. If they start having trouble, you're not going to get at them easily. So those become practical considerations that are going to drive the TRL. But you know, the concept of being able to just attach motors into the core of an engine is something that happens today.
And is Pratt Whitney investigating boundary layer ingestion technology?
We've certainly participated in studies in that area. It's clearly an early TRL. It's a very promising technology, but I'd say that's still some way off. You know, clearly a lot of work looking at it, but it's very much in the early stages of our advanced technology departments.
And obviously, you know, GoFly is so incredibly pleased to have Pratt & Whitney as the sponsor of the Disruptor Prize. The community is curious, what are you excited to see, and what are you looking for as you are seeking winners for this prize?
So that's the question that I thought I'd get number one, and and it's interesting because I think if I give an answer, then I must not be ready for disruption. So here, you know, to some degree, it's going to be the idea that we're not expecting. Mm-hmm. Almost by definition, if it's going to be a disruption, the originality and groundbreaking nature of the idea, and of course its practicality, is going to be something we're not expecting to see. Mm-hmm. So, you know, that's probably a somewhat unsatisfying answer for somebody who's looking to win that prize. But we'll know it when we see it, I think, is the answer. If I give example, I try to cover through the talk a range of things that we've viewed as disrupting in the industry. Mm-hmm. But as we get into it, I'm sure there's going to be something in these ideas that really knock our socks off, and that'll be the one.
So then along those lines, what advice would you provide to the teams at this particular stage? They are approaching the phase 2 deadline for the competition, where they will be providing some prototypes now at this point, where they'll actually be demonstrating their devices and providing videos and images of how their devices will actually work. And as they're working on that submission, as well as entering to phase 3, and as you know, planning for the final fly-off, your advice and comments for the teams on how they should be approaching their technologies at this point.
Sure. So, you know, first off, I think I touched on this in the lecture, you really know your objective in here. So there's a rubric, there's a set of rules for the prize. Mm-hmm. Meeting the rubric, it sounds obvious, but that's going to be number one to get in there. Now, once that's been done, there's a couple of things that become interesting, and these may fight against each other. Firstly, it's the practicality of the design. You start to think about, well, if it's going to be of value in the world, then it has to be something that could be deployed. So we'd be interested in seeing how those sort of practical considerations of cost and reliability and so forth actually sit within a design, again, that meets all of the basic requirements and satisfies those. The other part of it is how disruptive the technologies are that have gone into it, which may sort of fight against what I just said in the first place. So, the application of technologies that are not typically found in the aerospace world. That may be a key one. A new way of looking at the problem is going to be something that's going to excite us, because frankly, as the sponsor for that disruption award, the reason we come at that is we're interested in people who think differently and solutions that look different, because we can probably come up with solutions that look the same as the one we've done before. We need help thinking differently. So that's a key thing that we'll be looking for.
Mm-hmm. And in the history of disruptions in propulsion, what's the time that you've seen typically between the first idea and actual commercial application?
Well, that's a good maturation for technology. We look at this quite a lot. The TRL progression, it can vary widely, but it's going to be in years, typically, to go from those first early TRL ideas through to a TRL 6 level idea that's worth us getting into a product and developing it to go into service. The practicality of this is getting through the early TRL stages is often relatively quick and can be challenging, but not hugely expensive. Bringing those ideas up to a level that is safe, is commercially viable, and will get adoption and approval through all the agencies that need to support it, is where time starts to come into the equation, as does cost. I mentioned in the talk, the levels of safety and reliability in this industry are something that we're rightly proud of, and the structure of the regulations and the way we approach the task is designed to ensure we never dilute that. We're always working to maintain and improve on that environment.
So Geoff, last question then from the community is anything they should be wary of from the engineering perspective? Obviously you have a depth and breadth of experience here. Anything that they should be thinking about that perhaps they're not, that you can offer to them at this point?
I mentioned in there, I'll restate it because it's something that I think the industry, certainly that I've observed in the industry over the last decade or two, it's limiting yourself to, or not limiting yourself to the available manufacturing capability in the world. So, if you look at the history of some of the greatest companies in our space, they were founded on a manufacturing technology. So Sunstrand, who, one of the leading electrical generators manufacturers in the world, now part of Collins Aerospace, started off as a machine tool company, and really made their name making hydraulic automation for the car industry in the 30s. Rohr, a big nacelle manufacturer, again part of Collins, Frederick Rohr developed one of the early drop hammers that was used in shaping metal for airplanes. Their roots go back to manufacturing technology. More recently, we've got into design, and we've tended to look at the manufacturing landscape as a fixed technology that we design around. And we need to shift that to a place where we're continuing to challenge manufacturing capability at the same pace that we challenge design. So don't fix your design around what can be manufactured today. Go and challenge, say, I need to be able to make this shape. I'm going to go and invent the manufacturing technology that'll allow me to make the shape. That linkage is really important. So I'd encourage the teams to not look at this as just an aero design problem. It may be a manufacturing design problem. It's where things like additive manufacturing have really helped us to move forward, I think.
Yeah, great point. And I hope that the teams really heed that and consider that there may be something that needs to follow on what they create. So thank you so much, Geoff, for your time and for your lecture. Once again, we really appreciate Pratt & Whitney's partnership in the GoFly Prize, and we look forward to sharing more in the coming days.
Thanks so much.
Take care.